Hi everyone. Hello. Uh, Hi. So am I audible?
Yes, sir.
Is the screen visible to you?
Yes, sir.
Okay. Okay. So this is fifth class session. Okay. So before starting further, do you have any question or any doubt from the last session?
No, sir, I was not present in the last session.
Okay. Okay. And also, do you have any question or any doubt till now from assignments or from sir's lecture?
Sir, can you help me explain that how can we write Bayes category theorem? If you know, he has written three ways, and in one exercise, professor asked us to write the version of BCT zero similar to BCT two and
Can you please
BCT
bit
three.
louder? Actually, I'm unable to hear you properly.
Am I audible, sir?
Yeah. Yeah. Fine. Fine. Just a bit louder only. That's fine.
In one question, he asked us
Huh.
to write versions of Bayes category theorem
Mm-hmm.
0 similar to Bayes category theorem 2 and 3. I mean, they are the versions of the same theorem.
Huh. Okay.
So, if you can tell me how should I do it?
So is it in his lecture notes?
Yes, BCT 0, BCT 2 and 3.
Okay. One one. Sorry. One. Okay. Can you send the notes? Is it possible? Or can you just share your screen? Is that possible?
I will try to send the notes, sir. Just please wait 5 minutes.
Yes, sure. Okay, so there is a one student joined, Mr. Mustaq. Okay, Mustaq, do you have any doubt, any question? Okay, in case you have any question, please unmute yourself and let me know. So we have shared some link. Okay, one minute. Okay, in which page?
Yes, sir, telling one. It's in.
In which page?
Yes, sir, I'm telling you. It is in page number 61. Here it mentions the two theorems in other versions, and they ask us to write down versions of BCT0 similar to BCT2 and 3.
One minute. One page number 61. Written versions. BCT0 with P similar to BCT2 and 3. Huh? What is BCT0?
BCT0 is written here. Wait a minute, sir. It's written, it was written somewhere. This page number 60, I think it is BCT1. Yes, in the video it was BC. Oh, okay, it was page 59. 59, BCT0.
Page 59. Okay. Mm, हाँ, yes, every complement matrix is second category. Okay.
Sir, are these theorems used in later part of topology?
One minute. One minute.
Yes.
Actually, these things are part of the points topology part 2. I mean, the part 1 of this points topology, usually, I mean, if you follow any other textbook, then part 1 of points topology don't require these things. Okay.
think, sir, this is a bit confusing. Like, what exactly do they
Ah,
want
yes,
us to
yes,
write?
correct only. Yes, right. You are correct only. It is quite common. Uh, what? So is it like first count? Just wait for a moment.
Hello?
Yeah, Mustaq, tell me, Mustaq.
Yes. Yes, I can hear you and audible too.
Okay, thank you for confirmation. Okay, let me think. Just hold on. Here, that's a bit confusing, yes. But there is no other versions too. Uh, seven other versions, I don't think so. Oh, that I am sorry to say, but I am unable to figure out what exactly the question means.
It's okay, sir. Even I was not able to understand.
Because the problem is that the BCT1 and BCT2 are the equivalent definition of BCT0. So, what to write? Just hold a moment, please. So, there's a denseness is also there. Hold on. X is oh, no, that question I am unable to understand. Sorry.
It's okay, sir. They give us these kind of questions where I used to spend a lot of time of my day and then end up being silent.
I understand the problem. So you may ask, better you can ask this particular question to, better you can ask this particular question to us, the instructor, because this question, because I'm unable to understand what to write, what they're asking to write even, because BCT 2 and 3, this seems to be equivalent statement of BCT 1. Okay, so what is BCT 0? BCT 0 was every column second category. Okay. Uh, if exact union of this, then no, there is nothing to be written as per my understanding. So BCT is 2 and 3 and nothing but the equivalent discrepant of BCT 0. Okay, so there is nothing to be written. Understand? So I am unable to answer this question itself. Okay.
Okay, sir.
Okay, so do you have any more questions?
Sir, also I want to ask, like, I spend too much time trying to understand some of the things. So how can I speed up my progress
I mean,
while watching the videos?
some of the things includes what?
Like, sir, I watched these videos. For example, I was watching week 4. So, uh, for example, I was watching this lecture, Bayes category theorem. So while I was understanding the proof, it took me quite amount of time. So how can I like
So you are the one
speed?
who was from engineering background, am I right?
Yes, yes, yes.
Yes. Last session we have discussed now that you should follow some textbook also, right? If you follow textbook, if you take any textbook, for example, there is a textbook of topology called, sorry, textbook of metric space by Kumaresan and textbook of
MAPA.
topology by Mancres. So if you follow either of this textbook, you will find things go very smoother and easy.
Okay, sir. I haven't tried yet. Okay.
No, no, I mean you should try because those books are written from a beginner's point of view. Now, since the beginners of this kind of subject, so you should look into those textbooks. Those are very easy to read, easy to understand, and interesting way it is written actually. Okay,
Okay, sir.
yeah, and in Mancres, either in Mancres or in Kumaresan, you can blindly follow any of these two books, and you will get a grasp of this subject, as well as it will help to build intuition, not just going theorems and proofs. It will help you to build intuition. Okay, and the point is that, by the way, in engineering you are in which stream?
Mathematics and computing.
Okay, so there is, I mean, I don't know is it within your scope or not, but there is a subject called topological data analysis. Okay, and if it is possible, you should try that subject too, because it's a really a hot topic nowadays, and placements are good in the subjects. And I mean, the point is that there is a very good amount of exposure in topological data analysis. Okay, so simultaneously you should know those at least basic things of that subject. Okay, understand?
Okay, sir.
Yeah. Okay, do you have any more questions? Does
No, sir.
okay, anybody, other students, do you have any questions? By the way, I have shared a Google form link. Please submit that Google form. It will count taken for attendance only. So please don't forget to submit that form. Okay, so any other students, do you have any question or doubt? Please let me know. Mm. Okay, so if nobody have any questions, so what to do? So there is, so let me then, in that case, let me start with um, connectedness, from where we have started, we have stopped at last class. So okay, 1 minute. So the question, so So in last session we have seen we in last session we are doing some kind of characterization of connectedness, right? So today we shall finish this. So there is one characterized connectedness, namely suppose X is a topological space. Okay, one. Then X is connected if and only if for any function f from x to plus minus 1 is constant. So X a topological space. It is that a topological is connected if we take any function from the space to doubleton set. Not only doubleton, it will be discrete. Instead of doubleton, you can take any, or you can take any discrete set is constant. So in that case, it will be connected. It will serve as an characterization of checking connectedness. Okay. So can you please think and try at least to do one direction? So let's try to solve the one direction first. So suppose let X is connected, and then show that the image of the function is constant. So please take your time, think about it. So first let's assume that X is connected, and from that try to show that that if you take any continuous function from, of course this continuous function, I somehow forgot, but it is continuous. Any continuous function f from X to doubleton set is constant. So try to do it. Remember that in the last session we have seen one thing, namely continuous image of connected set is connected. So you have to use that fact here. So please try to use that fact. Take your time. So anybody able to solve it, or at least how to? I mean, this is very easy actually. So there is nothing to think too much. So anybody please try, or anybody please unmute yourself and tell me how to solve this.
Sir, one guess attempt.
Yeah.
Like we can use the contrapositive to prove this.
Okay.
Like if we assume that say x is not constant, Now we will prove that say x is not connected. Now we will prove that f is not constant. And similarly, we will assume that f is not constant. Now we will prove that x is not connected.
Mm, okay. Okay, how to do? Okay, how to do that?
Okay, say if that say x is not connected. So there must exist, by definition, two or more uh, disjoint open
Okay,
sets
so one
whose
thing. So
union.
one minute. So there are two direction of this proof of this theorem, right? So
Yes,
what direction you want to prove first?
let's say we prove that x is connected implies
Hmm.
x is constant. So we take the contrapositive that um, oh okay, so its contrapositive is that if x is not constant, then it implies that x is
No,
not
no.
connected.
Contra. So you want to show that x connected implies f constant, right? This is what you
Yes,
want to show. So the contrapositive statement will be f not
will be that
constant implies x not connected.
x is not connected. Yes,
So that means what? You have to assume that there exists some f which is not constant, and from that you need to show that is not connected, correct?
yes.
Yes. So yeah, so give the argument.
So if such an f exists, so
One
in the
minute, I'm writing
pre-image
down.
in the
Okay.
pre-image of 1 there will be some set say u, and in pre-image of -1 there will be some set v, and u union v will be x. So this means x is not
Why
connected.
why u and v are open?
Oh, oh, this I did not think.
No, that's okay. You did not think, but it is true to be open. There is no problem. But why they are open?
Mm, that I don't know, sir.
See, the point is that minus one and plus one. This constitutes plus minus one, right? Correct. And singletons are always closed, correct?
Oh, so their
So
pre-image will
their
also be closed.
yes. Now singletons are closed, and so their complement. So one complement is minus one, and similarly minus one complements are one. So that's why both singletons at plus and minus one are open. Is it clear?
Oh,
Singletons closed, so their complements are open. So that's why plus and minus one both are open. So the UV both are open set. And so x equal to f inverse u union f inverse v. And of course f inverse of u intersection f inverse of v, that is f inverse of u intersection v, that is empty, because u intersection v, this part is empty, correct? Sorry, there it should be u and v only. Sorry, 1 minute, it is not f inverse u intersection v, it is what? So x equal to f inverse minus 1 union f inverse plus 1, correct? And f inverse minus 1 intersection f inverse plus 1, that is of course empty. Okay, so that's why a and b I mean these two sets inverses forms what? Forms a separation of this space. Is it clear?
yes.
Okay. So this is one direction that tells that x constant implies x connected implies f constant. So you have used the contra positive statement, but without using that directly, we can do as follows. So we can, I mean, the point is that if, I mean, the point is that since x is connected, so this implies what? One minute, it's got this implies what? F of x, it is also connected. Why? Because as f continuous, correct? Now since f is continuous, so that implies what? I mean fx is connected, but this f of x is subset of plus minus 1. So this implies what? Either f of x equal to plus 1 or f of x equal to minus 1. Is it clear? So that is that f has to be connected. So this is another argument of this thing. Is it clear?
Yes, sir.
So this tells what? This tells that f, so that is what? X connected implies f constant. Okay. Now I am asking the reverse. Suppose f constant. You need to show that x connected. Let f constant. We need to show x connected. Please try to do. For this direction, you need to do contrapositive. You need to apply method of contradiction. That means what? You need to assume that x is disconnected, and you need to construct a function which takes both of the values plus 1 and minus 1. And for that, you need to use gluing lemma. And I mean, these are the facts you need to use simultaneously. So think about it, take your time, and please solve it. It is not difficult now. Please think and let me know. It is not difficult now. Anybody are able to solve it? Anybody able to solve it? Okay, so let me explain the argument as follows. So it's a contrapositive way of solving. So let x disconnect. So that implies what? X admits a separation. Sorry, x admits a separation u phi. Okay. Now we are defining f from x to plus minus 1 by x going to plus 1 if x belongs to u, and minus 1 if x belongs to v. And the point is that u and v are both closed set, being a separation. So this implies by gluing lemma, sorry, f is continuous. So this tells what? This tells if x is disconnected, we can have a function from x to plus minus 1 which attains both of these values. So that is the argument of, that is the way of solving this problem. Is the argument clear to everybody? Please let me know.
Yes, sir.
Okay. So okay, so I hope everybody understood this argument, this solution. So this particular theorem tells what? This particular theorem tells, gives a criteria for checking connectedness. Okay, so okay, so now let me show you the utility of this type of function. Okay, so okay, just hold a moment, let me think a moment. Okay, so let me demonstrate a utility of this type of functions. So first theorem or first fact is that, or you can say the application. What is that? Oh. First application is that let x and y are connected. Show that x cross y is connected. Okay. So that's what you need to show. So now, So that means what? You need to show that is it is equivalent to, by the previous theorem, it is equivalent to showing that any continuous map f from x cross y to plus minus 1 is constant, correct? That's what we need to show. Now please try to use the previous theorem and the properties of the connectedness of x and y and try to show that any continuous map f from x to x cross y to plus minus 1 is constant. Okay, so please think, take your time and let me know. It is very easy to do, so there is nothing too much to think in a complicated way. So please try to solve it by yourself. Anybody please try. Okay, so let me do it. Hold on. So choose x naught y naught belongs to x cross y. Okay, and we have this function f x cross y to plus minus 1 given. We need to show it's constant. Okay, what we can do, we can consider these two functions. I mean, the point is that we need to create function from x to plus minus 1 and y to plus minus 1 from the given function f from x cross y to plus minus 1, right? So one way is to do the compose with the inclusions. So we choose a arbitrary point x naught y naught and we need to show f of x naught y naught is equal to plus 1, or maybe we need to show that if we have one, if you are 1 plus 1, if I mean if x naught y naught is plus 1, then x prime y naught x prime will be plus 1. That's what we need to show. Okay, and x prime y prime, to show if x plus 1, then f of x prime y prime, that is also plus 1. Okay, that's what we need to show. Okay, so what we can do is that we can take this function I1 x I1 x is equal to x comma x naught, and I2 of y is equal to, sorry, x comma y naught, and I2 of y is equal to x naught comma y. Okay, so these two are the functions from x2 plus minus 1 and y2 plus minus 1. So that means if composite I1 and if composite I2, these two are constant. That implies uh, f of x comma y naught is constant for all x, and f of x naught comma y constant for all y. Okay, so what you can assume is that we can assume f of x comma y naught is equal to plus 1, and f of x naught comma y now. Okay, so now the point is that, so this tells that f of x comma y naught, sorry, f of x comma y naught and the function f of x naught comma y both are constant. So I mean, now the point is that so okay, so if f of x comma y naught is equal to plus 1, that implies f of x naught comma y naught is equal to plus 1, and this one, if f of x naught comma y is equal to minus 1, this implies f of x naught comma y naught is equal to minus 1. Okay, so that tells what? That tells that the value of these functions f of x comma y naught or f of x naught comma y, although both are constant but both are same. That means what? That is f of x comma y naught is equal to f of x naught comma y for all x comma y, and this is a constant. Okay, so let it is plus 1. So this implies what? This implies f of x prime comma y plus 1, and this implies what? This implies f of x naught comma y prime is equal to plus 1. Okay, and hold a moment. So both are plus 1. We need to show that f of x prime comma y prime, this is the constant function. Okay, that's what we need to show. Hold on. x prime comma y naught prime comma the function is constant here, so x naught comma this function is constant here, prime comma okay. Okay. Okay, so the argument goes about it. Okay, now the point is that, okay, so we have two informations, that f of x prime comma y naught 1 and f of x naught comma y prime is equal to plus 1. Okay, now first look at this information, f of x naught comma y prime plus 1. Okay, if you look at the graph, it will give the x naught comma y prime is this particular point. Okay, and this particular point is coming this line and this line intersection. Okay, now the point is that we can constant a function f from y to from y, I mean f prime, I mean f. I mean the point is that we can construct a function g from y to plus minus, sorry, x to plus minus 1, where x is going to f of x comma y prime. Okay, now x is constant, sorry, x is connected, is given, so g constant, but it is given that f of x naught comma y prime equal plus 1. That means what? F of x comma y prime is equal to plus 1 for all x. That means that is x comma y prime is a full this line. Okay, similarly, what hmm. So what, yeah, similarly, f of x prime comma y is equal to plus 1. Which was the x prime comma y? X prime comma y is equal to this one. So this one is also plus 1, as well as this one is also plus 1. So their intersection, this one, which is nothing but x naught comma y naught, sorry, x prime comma y prime. So that tells the, so this tells that f of x prime comma y prime is equal to plus 1. So that was our target. So initially we assume that f of x naught comma y naught plus 1, then we need to show that f of x prime comma y prime is plus 1. So this tells that f is a continuous. If is a, so f is, so x cross y is connected. So that is the argument. So is the argument clear, or should I repeat the argument? Please let me know. So please let me know, do I need to repeat the argument?
No, sir, it's clear.
Okay. Okay, so this particular theorem x cross y connected, given that x and y is connected. So without using this particular fact that any continuous map from that space to doubleton set is constant, without using this fact, you can prove it from definition, but that is also very difficult. So this technique is very useful for solving problems also. Okay. So for example, so let me show you an example. I mean, a theorem which can be done in two ways, so that you can see that. I mean, so you can see, you may feel which one is better or which one is not good. Okay. So let me take the question first. Okay, 1 minute. So the question is as follows. Let E alpha be the collection of connected subspace of X, and let A be a connected subspace of X. Show that if A intersection A alpha non-empty for all alpha, then A union of union A alpha connected. So before giving you the proof, let me show you the intuition why this is even true. Okay, so the point is that uh, so suppose these are all A alphas. Okay, this is A alpha 1, A alpha 2, A alpha 3, dot dot dot, and we can consider circle like this, and this circle sorry, and this is nothing but our A. So these are lines are A alphas, and this hexagon is our A, and clearly each A intersection A alpha is non-empty. So this picture tells that the union is clearly connected. Okay, so that's how the intuitively it is clear. Now the question is how you can prove it mathematically. Okay, so it can be done in two ways. Okay, so first try to use the definition to show this. Take your time, let me know. First target is try to use definition. That is the one way. Please try. Take your time, let me know. This is the first way of solving this kind of problem. Please try to solve it. So please try to use it from the first definition. Anybody are able to solve it using definitions only? I mean, whatever you have in your mind, you can please tell. There is no issues.
Sir, one attempt I can try.
Yeah, sure.
I can say we can prove this by contradiction. So
Yeah.
we assume that A union A alpha union all is disconnected, then this set can be written down as union of disjoint open sets U and V say, and if that is
Let me
possible,
write it down. So you are assuming that that union is disconnected. So that means there exists a separation. Okay. Then
then I think we will arrive at contradiction that there must, if this is the case, then there must be case that either A alpha, some A alpha is disconnected or A is disconnected. That we have to think how we can create the link.
you are the correct direction. So let me show you. So anyway, so this is equal to union P and U and V are separation of X. Okay. Now the point is that A and A alpha, all of these are subset of this union, correct? And these are all connected. So this implies what? This implies A subset of U or A subset of V and A alpha subset of U or A alpha subset of V. Is it clear why it is so? I mean, A or A alpha, since both are connected, so each of them can lie either of U and V. It cannot lie within both. Is it clear? Because this particular theorem we have seen in the last class, right? Is it clear that why this is so? This is the first option. This is the first implication. I mean, if you are unable to understand, please tell me. I mean, is it clear to you that whether A subset of U or A subset of V or A alpha subset U or A alpha subset V, either of this, is it clear to you? If not, please
Sir,
tell me. Yeah.
how did we arrive at this? That say A and A alpha are connected, so that would imply that A and A alpha both would belong to only one of them, not both.
Correct, correct.
Okay,
Yeah.
okay.
Okay. So that is the first observation. Now the point is that suppose A subset of U, then then hmm, E alpha must lie within V. Sorry, within U. Why? suppose A lies within you, then A alpha also must lie within you. The question is why. So any idea why? I mean, just you need to use the given fact of the statement of this theorem. So nothing extra has to be used. So you can do contradiction, contrary method of contradiction. So suppose if A alpha subset of V, then what problem will be there if A alpha subset of V?
In that case, A union A alpha would be disconnected.
Mm. Why?
Um, A belongs to U and A alpha belongs to is a subset of V. That is why.
But that's what I mean. A union A alpha is disconnected is same as saying that whatever we are trying to prove, they are put if you alpha equal to 1, then we will get A union A alpha, right? So we cannot use that, right?
Oh,
So if A alpha subset of V, that implies what? A intersection A alpha subset of U intersection V. But U and V, this forms a separation. So that means what? U intersection V is empty set. So it is U intersection V is empty set. But the given condition of this theorem tells that A intersection A alpha is non-empty. So that's why A intersection, that's why A alpha subset of V, and this has to be true. There is no other option. Is it clear?
it was U, right, sir?
Sorry, it was correct. So till now we get that A subset of U, A alpha subset of U. So this implies what? A union of union alpha A alpha, this lies inside whole of U. Okay. But initially we assume that this is equal to U intersection phi and U V and separation. So this implies what? This implies phi is equal to empty. So, but such a thing is not true, because for separation V has to be non-empty. So that is the contradiction. Is the argument clear?
Yes, sir.
Yeah. So this is one way of showing that what showing that U that I mean one way showing that A union of union alpha A alpha connected. It is one way. It is from the scratch, from the definition. Now another way of showing is to use that function method. What is that? Huh? So that means what? So let F A union of union alpha A alpha 2 plus minus 1 be any continuous function. Okay. We need to show it is constant. So that function f restricted to a, this is constant, and as well as a function a restricted to a alpha, also constant. Okay. So if, because a and a alpha connected, so if f restricted to a is equal to plus 1, That implies if restricted to A alpha, this has to be plus 1. Why? If restricted to A is plus 1, then if restricted to A alpha, that will also be plus 1. Any idea? Any guess why that has to be true? Think about it, take your time. It is very easy.
Because A intersection A alpha is non-empty.
Correct only. Absolutely. As A intersection A alpha non-empty. Now, since both A and A alpha, the restriction of is plus 1, this implies what? Of course, this implies if restricted to union alpha, A alpha is equal to plus 1. So, in that case, combining this and this together implies f is equal to plus 1. So, that tells that f is a constant function. Is the argument clear?
Yes, sir.
Yeah, so as you have noticed that no sooner we use the function method, the process of showing connectedness becomes much more easier. So that's why this method has an advantage of showing something is connected. So that's why in exam also you can use this method for solving, for showing connectedness. Okay. So that's what the thing is. So similarly, there is another problem. The question is that let an be a sequence of subspaces of one minute, let me write it down. Let n be a sequence subspace of n such that an intersection an plus 1 is non-empty for all n. Show that union of n is connected. So intuitively what is happening, suppose we have a1, a2, a3, a4 and dot dot dot, all are connected, their union is of course connected, there is nothing, I mean, this is quite obvious. So how to prove this? So please try to do yourself, because this is the same problem as the previous one. So please try to do yourself first. Okay, I shall be back within a few moments. Anybody able to solve it? How to process? I mean, yeah. Anybody able to solve it? Please let me know. Okay, so we can do this as follows. Okay, so as per you have seen from the previous problem, this can be solved by two ways. Okay, so this particular problem can be solved two ways. Let me demonstrate the two ways as it is. Okay, so first way of solving this problem is from the definition itself. Okay, so this first method is using definitions. Okay, so let union n disconnected. So we can write union n of an is equal to C union D, where C and D is a separation. Okay. Now each an sub of union n, that means n subset of C or n subset of D for all n. Suppose A1 subset of C, then we must have A2 subset of C. Why? Because otherwise A2 subset of D, this will implies A1 intersection A2 empty. And now A2 subset of C, this implies A3 subset of C, and so on. That is AN subset of C. Okay. Now no sooner AN subset of C for all n, that implies what? Union of AN sub of C, and union of AN is equal to C union D. So that implies what? That implies D is equal to empty set. But of course, that is not the case. So this tells that union of AN has to be corrected. So this is one way of solving this problem. Now let me show you another way of solving this problem. Okay. So okay, so is this okay? So the method using the definition is clear.
Yes, sir.
Okay. So now we can apply the method using the function. Okay, so please try to apply the second method using functions. That is, you need to assume that you need to start with a function. So you need to start with the function let f union n to n be continuous form. So union a and n to plus 1 is continuous. You need to show that f is constant. Okay, so try to prove this by yourself. We need to show that f constant. So unlike like the previous problems method, say, two, here also the say almost same process will work. Please try to solve and convince yourself that it is indeed true only. Take your time. So are you able to do it? Anybody able to solve it using the function method? Okay, so the process is same. Let me show it to you. Yeah. Okay. So the point is that since a n's are connected, so f restricted to a n for all n are constant. It's obvious because all n are connected, correct? So this implies what? This implies that, I mean, okay, so suppose f of, so all are constant, okay. So if f of a1 is equal to plus 1, then f of a2, this has to be plus 1. Why? Because otherwise a1 intersection a2 could become empty, correct? So this tells that if we go on, this tells that f of an is equal to plus 1 for all n. That implies what? F, the which is a function from union n to plus minus 1, is the constant function, okay. So that's what the argument is it clear? I mean, this is almost same as the previous problem, but anyway, is the argument clear? Please let me know.
So I have one doubt.
Yeah, tell me.
In the application, like when x and y are connected, to show that x cross y is connected, I'm using this any continuous map f from x cross y uh, converges to plus or minus 1 is constant, right, sir? But all other numbers are constant. Why we are choosing 1 and minus 1? Why that function need to map only to 1 or minus 1? What
Okay,
is
so
there?
instead of 1 minus 1, you can consider any uh, discrete set also. There is no issue with that. I mean, the point is that if suppose you have function from a space x to some discrete space means disjoint amount of points. So b, since the space is connected, so its image will only inside one point, right? So if it is one, if the codomain is plus minus 1, it may be three distinct point, call it a1 a2 a3 a1 a2 a3. In that case also the same argument will work, okay. I mean, instead of two distinct point, you can consider uncountably distinct point also, but you will get finally the same thing. It will be a constant function. That's why, for sake of proving theorem easily, we simply take 2 point. Okay, are you understanding my point?
Is there any particular reason for choosing one, sir?
No, one has nothing to do with the entire argument. Instead of plus minus 1, you can take a comma b also, okay. So it has nothing to do.
Okay, sir.
There is a reason for plus and minus 1, because plus minus 1 forms a group under the operation. And the point is that in the case when the capital X is a topological group, in that case the map X to plus minus 1, there is a possibility of becomes a homomorphism. That's why it is plus minus 1. But for topology perspective, plus 1 minus 1 has nothing to do with the entire argument. Instead of plus and minus 1, you can take a1 and a2. Okay. So absolutely no issue with plus and minus 1 specifically. Is it understand? Are you understand?
Yes, sir, I understand.
Yeah. Okay, so the last problem tells that if all n are connected, the intersection is empty, non-empty, then the union is also connected. So there is, so I hope it's clear. Now, hold a moment. So all of you can remember the what does it mean by lower limit topology? I mean, what is the open set? What is the basis basically? Can you remember? Can you remember what's the basis for lower limit topology?
So can you repeat the question?
Yeah, what is the basis for lower limit topology? R suffix L, this denotes the R with lower limit topology. What are the bases? Can anybody please remember? What are the bases? Okay, so R suffix L, the basis elements are of the form closed interval A, open interval B. Okay, so this is a basis element. So any open set U is the union of these basis elements. Okay, so that's fine. So the question is that is R with lower limit topology connected? Please think. Please take your time. That means what either we need to show that it's connected, or we need to show that R suffix L can be written as union of two open sets. Any idea? Any guess? First, you have to guess, of course, right? Any idea or guess? Anybody?
I think it should be connected.
Yeah, any idea or any guess? Okay, so the first hint is that it is disconnected. It is true that it's disconnected. So now please try to find a separation U and V. So you need to find the U and V. Okay, so please do that or have a guess at least. Any guess or any idea, please?
Sir,
Yeah.
no, I want to ask something. Is say open interval minus infinity to say zero, uh, open. Is this an open set in lower limit topology?
Yes, you are correct. But why? I mean, how it is open?
No, I was asking you because
Yes.
say if we define minus infinity to zero, this and lower zero to infinity,
So 0 to
these two
infinity, open 0 or close 0?
close zero.
Okay, you are correct. Guess is correct. But the question is, you need to explain why both are open sets in R to low limit topology. See, the point is this minus infinity to 0, this can be written as union of a comma 0 with a is less than 0, and so and each interval a comma 0 is open, correct. And the right side 0 comma infinity can be written as union of a comma sorry union of 0 comma b is greater than 0, and each of these is open set. So that's why minus infinity 0 and 0 comma infinity closed, these both are open in with lower limit topology. So what do you understand?
Basically, we used the arbitrary union property.
Correct only, correct only.
Okay.
So now okay, so now the next question is that, so we have seen the notion of what, finite, I mean cofinite topology, correct. Cofinite topology means that complement are finite. So the question is that, let me write it down. So the question is that, let X be an infinite set with cofinite topology, with cofinite topology, to show X is, I mean the point is that you need to show that whether X is connected or not. Is cofinite topology is connected or not? That's what you need to show. Okay. So please try to guess. I mean, okay, so there is, it's difficult to guess. So the answer is that it is connected. Now it is your task to prove that's how to show that it's connected. It is known to be connected. So I'm not, I mean, so it is difficult to guess otherwise.
We can do this by contradiction.
Yeah, sure. So what is the argument?
Say that if they are disconnected, there exist two open sets such that the infinite set can be written as U union V. Now, since U and V are open, X minus U should be finite and X minus V should be finite.
So X equal to U union phi. Okay. Then
Yes.
yes, I add X minus
And
U finite and X minus V finite. Then
since and U and V are also U intersection V is empty. So
Hmm.
I think we will get from this only.
Yeah, intersection be empty, then what? I mean, where is the contradiction coming, right? There has to be some kind of contradiction, correct?
I think it will be on the lines of this only.
Yeah, you are almost near. So the point is that U and V are separation. So U and V both are open as well as closed. Okay. Now since U is closed, so that implies what? Uh, X minus U is finite. Sorry, since U is closed, this implies what? U is finite. And phi closed, that also implies V finite. Till now, is it clear that why they are closed and why closed implies finiteness?
Yes, sir. It is
Yeah,
by the definition of closed
correct,
set, right,
correct.
sir?
So that implies what? E union V is finite, but E union V is X, but X is given to be infinite. Sorry, X is given to be infinite. So that's what the contradiction is. Is it clear?
Yes, sir.
Yeah. Okay. Okay. So that's what it is for today. So if you have any question or doubt, you can drop an email. You can ask me, or you can drop an email. I shall get back to you through email also, or you can ask me in the next session also. Okay. And please don't forget to submit the attendance. Okay, I am leaving the session. See you in the next Sunday.
So where is this attendance link?
In the Google chat. In the Google chat, there is a Google form, and that's the attendance link. Do, do you get it?
No, sir.
In the chat, in the message box. I mean, do you get it?
No, sir. There is no messages in the in-call messenger. Can you resend it?
How? I mean, oh, 1 minute. 1 minute. Now, do you get it?
Yes, sir.
Yeah. Please submit the attendance. Okay, I'm leaving the session.